Welcome back to Natural History of the Pacific Northwest. I'm your host, Abe Lloyd, and we're at Larrabee State Park here on a very windy spring day. And I like bringing students to Larrabee because there are so many different types of beach. You can see on my right here in the background, there's a nice gravelly beach. We have a lot of gravelly beaches in the Pacific Northwest simply because we don't have the type of waves to churn up a lot of sands. So we typically only get sands when we're next to a river. So we have this pocket gravelly beach here at Larrabee. And then we also have a really nice rocky beach here at Larrabee. And then beyond the rocky beach, we can see that there's a nice sandy pocket. And when in protected deep bays, we often get sands just because the waves and the water and the drift cells are capable of carrying those sands until the drift cell ends, and here in this pocket bay we get a lot of sands. So anyway, we're going to explore these three different beach types: the gravel cobbly beach, or gravel pebbly beach, the rocky beach, and the sandy beach. Look at the natural history of different organisms with a particular focus on tide pools here in the rocky beaches at Larrabee State Park. And then when we finish that, we will explore a few of the shoreline types. So the steep cliffy shoreline, we have a lot of interesting plants. And then this bluff here is what's called a feeder bluff, and we'll look at some rocks growing on that feeder. There's some plants growing on that feeder bluff. In each of the habitats, the pebbly beach habitat, the rocky beach habitat, and the sandy beach habitat, there is a spectrum of life that exists in the intertidal zone between the lowest tide and the highest tide. And today we actually have a good low tide. It's a minus tide, something like minus 1.3. And I think it'll be low in the next hour or so. Starting with this rocky intertidal habitat, we're going to be looking at tide pools. And here we see a very shallow tide pool that's near the high end of the intertidal zone. And I'm going to teach you how to use some measurements, some tools for measuring things like salinity and dissolved oxygen. And we're going to compare the abiotic variables and the life, the biota here, between this relatively high, shallow intertidal or tide pool and another tide pool that's deeper and lower in the intertidal zone. So one important abiotic component that really controls a lot of life in the along shorelines is salinity. So many organisms need full concentration salt water because that's what they've adapted to. But here in tide pools, things might get a little less salty on a rainy day. Or if there's a lot of evaporation in some parts of the world, you can get water that's hypersaline when it doesn't exchange with the rest of the sea very much. So the tool we're going to use for measuring salinity is this thing called a salinometer. And it's just uses the properties of light diffraction. So we take a drop of water, we put it on this screen, and then there's a blotter here that blots out that water. And now all I have to do is look through this, and there's like a discontinuity between a blue color and a light blue color, and it's showing me that the water is 34 parts per thousand salt. So in the open ocean, actually, here in the Northwest, this water is usually about 35. So we haven't had any rain, and this probably got flooded by the last high tide. So that's why the water here is pretty salty. In reading the salinometer, I could see that there are two scales. And the scale on the right is the one we're going to focus on. It reads from 0 to 100. And in this case, the discontinuity was about 34. And that discontinuity marks the where on the scale we take a reading. And then there's a symbol to the right of the scale that looks like a percent sign, except it has two zeros on the bottom, and that just means parts per thousand. Now the scale on the left reads from 1.000 on the bottom up to 1.070 on the top. And then on the left of that, it says D2020. And essentially, this is a density measurement, or the density of the water. We know that fresh water has a density of 1, and salt water gets more dense than that. So in this case, the water would have a density of about 1.025. But most people report salinity as parts per thousand, and that's how I'm going to teach you to do it. So for this particular salinometer, we would be using the scale on the right. Another tool that we could use to measure some abiotic factors is a pH tester. And so this thing has a bulb that we're going to stick in the water, and you'll notice when I uncap this that in the bottom there's a piece of wet paper towel in the bottom of this cap, and that's to keep the bulb wet. If your cap is dried out, it's quite possible that you need to recalibrate it. So I simply turn this on and swirl it in the water, and I'm going to need to wait for it to stabilize. Looks like it's starting to at 9.4 and climbing, 9.5, climbing. All right, usually I give it about 30 seconds. So it looks like it's stabilized at 9.73 or so. 9.74. Okay, we'll call that good. So what does that number mean? pH. Well, it's an indicator of the acidity or the alkalinity. So you'll recall that 7 is neutral, and above 7 is alkaline, and below 7 is acidic. And seawater is almost always alkaline. So we care about pH because the oceans are getting a little bit more acidic with increased CO2 in the atmosphere. So some of the CO2 actually dissolves in the water, forming carbonic acid, and you've probably heard of ocean acidification. We can measure ocean acidification with a pH meter. The next instrument I want to teach you how to use is this thing called a dissolved oxygen probe. And it has a sleeve that protects the sensor, so you want to make sure you take that off or you're not going to get any readings. And like the pH meter, there's a damp paper towel on the bottom to protect the sensor inside this stainless cage. You can see the yellow sensor. Okay, so I start by putting it in the water, making sure that the instrument is on. And then it'll usually take about 30 to 60 seconds for the readings to stabilize. So this instrument tells me 3 different pieces of information. On the top, it tells me the milligrams per liter of dissolved oxygen. It's an absolute measure. In the middle, it tells me the percent saturation. And on the bottom, it tells me the temperature. There's a relationship between temperature and the amount of oxygen that water can hold in solution, dissolved oxygen. So warmer waters hold less oxygen, and colder waters hold more oxygen. That's why stream restorationists plant trees along riparian areas, because the trees shade the water and keep the water cold. So interesting here, let me read you the numbers now. So we have 14.7 milligrams per liter of dissolved oxygen. Just an absolute number, we can compare that to another pool. Now the percent saturation is roughly 157% saturation. Now that's odd. How can you have more than 100% saturation? Well, it turns out that this tide pool is really shallow, and so it can change temperature pretty quickly. And last night, or yeah, probably last night when it filled up with the cold ocean water, it was holding a lot of oxygen. And now sitting here in the sun, it's shallow, it's warming up quickly, and it could actually warm up faster than the oxygen comes out of solution. So we have hyper saturated water right now. But if this water were to stay at the 19.4 degrees Celsius for another 5 hours at this temperature, we would see that percent saturation number fall as the water gasifies the oxygen, comes out of solution. Okay, so we actually have lots of dissolved oxygen in this tide pool, despite it being 20 degrees Celsius, which is, you know, I could go swimming in this. Wouldn't go swimming in the ocean right now. So there are two other ways that oxygen can get into water. One is that plants, which take CO2 and through photosynthesis produce oxygen, aquatic plants can oxygenate the water during the day when they're doing photosynthesis. Another way that oxygen can get into the water is through the surface. And right now, if I agitate the water, I'm increasing the surface area, and that speeds up the process of either oxygen going into the water or leaving the water. So I could rapidly reduce the percent saturation of this. Look, it's actually happening. It was 164, now it's 163. Now it's 165. Anyway, I increased the, by increasing the surface area, I can increase the gas exchange rate. Okay, now we're going to do a quick biodiversity survey of this tide pool that we could compare to the deeper tide pool. And I have this great book called Marine Wildlife with the San Juan Islands and the Puget Sound, and it's a good resource because it includes birds and seaweeds and invertebrates and algae, so we got the whole spectrum. Okay, so what do we have here? I see some rockweed, I see some sea straws, so two different seaweeds. I see this red algae, not actually sure what red algae that is. The reds can be pretty difficult. And then over here, in here, we got this green seaweed that is called sea lettuce. So I actually have our three major types of algae. The greens are in the green algae group. The sea lettuce is in the green algae group. This rockweed is in the brown algae group. A lot of our kelps are brown algae. And this is a type of red algae. So only the greens are close relative to plants. The others are in totally different phyla, kingdoms, I think. All right, so we also have some crustaceans. We can see some barnacles feeding here. The barnacles are a sessile invertebrate. They attach to the rock, and they feed on plankton, and so they filter the water with what most people call their foot that has a bunch of feather-like appendages on it, so they strain through the water, capturing plankton. This tide pool also has quite a few little hermit crabs, and this hermit crab has used a small snail shell for its home. Oh, it's about to escape. So here is a bay mussel, and mussels are often found pretty high in the intertidal because they will get eaten by starfish if they're too deep. The starfish avoid getting high in the intertidal because they'll get eaten by seagulls, so there's a whole food chain going on here. Mussels are also filter feeders. They can't close their shells super tightly, so if they get too high, way up high, then they'll be exposed too long by low tides and they'll dry out and die. So there's a delicate balance that mussels have to face. All right, now we're gonna go to a low tide pool. There's a real good one I remember out here on the point. This tide pool is bigger and it's also closer to the water here. It's lower in the intertidal zone, and so I think we're going to see some differences in abiotic factors. Because it's lower, it's going to get flushed with seawater more frequently. Because it's bigger and deeper, the water in the tide pool is going to stay cooler. So those are abiotic factors that we can measure, and let's get out our tools and take some measurements. Okay, we'll start with dissolved oxygen this time. And so the small tide pool was around just under 20 degrees Celsius, and I'm predicting that this is going to be colder because it's deeper and bigger and closer to the ocean. Look at that, 13.9 degrees Celsius, so quite a bit colder. And we have looks like right around 12.25 or so milligrams per liter of dissolved oxygen. So that's the absolute amount of dissolved oxygen. And the percent saturation is about 114. So remember the last tide pool, the small tide pool, had something like over 150% saturation of oxygen. And this is just 115 or so. So because this has changed temperature less, it's warmed up less, it isn't as oversaturated. All right, so that's dissolved oxygen and temperature differences. Now let's look at differences in salinity. I would anticipate that there won't be any difference in the salinity measurement because it's not raining and evaporation isn't really a big deal. So it looks to me like it's at 32. The last one was 34, so marginally different. We'll do pH again. Steeper tide pool. Looks like it's about 8.47. Remember that pH, the CO2 can affect pH, so in the shade, when plants are undergoing the dark cycle, they're actually metabolizing and producing CO2, so they can actually change the pH of a body at night in a small contained space. Time for our biodiversity survey. We could start with some seaweeds. So one I just pulled out of the water here is called bleach kelp, and if you break this and smell it, it has kind of a bleach smell to it. Cyanidus is the scientific name. Yeah, what else? We got the same sort of, or a similar red mossy algae here, and then some of that green sea lettuce, and a little bit more rockweed down there. How about animals? We got Let's see. Oh, a hermit crab. I thought these were whelks, but it looks like they've been used to be whelks, and now hermit crabs are inside. Let's see if any of them are whelks. Another hermit crab. We got more barnacles. Let's see, over here we got more mussels. So some of the same animals. Here's a whelk. You can see that's the foot that it uses to move along as it grazes on seaweeds. So part of the reason that we don't have a lot of seaweed in this tide pool is probably because there are many whelks eating it. Oh, and here's something kind of cool. This is what's called a jingle shell. It's attached to the side of the pool, and they traditionally are used on regalia because they jingle. Like, they're also pretty on the underside, but I'm not going to pull it up because that would kill it. All right, we also have a tube worm right here with the white tube and the red top. This bigger tide pool seems to have a bit more biodiversity than the smaller tide pool, and it could be due to differences in the abiotic factors, or it could just be due to the fact that it's a bigger pool. And we know from the theory of island biogeography that when you have a bigger habitat patch, you tend to have more diversity, because within that habitat patch there are all sorts of microhabitats that can support more animals or organisms. Okay, next we're going to move to a sandy beach and look at some of the life found on a sandy beach. Ready? We have a nice low tide, and this mud flat is exposed, and maybe you could see some clams shooting up water. There was one. You can see a lot of eelgrass. This is an environment that we only really get to see at the lowest of low tides, and today is a nice good low tide. So I brought along a trowel. We'll dig through some of this fine sediment and look at what we find. As I mentioned in lecture, one big difference about the mud flats is that there's nothing for things to attach to. All the sediment here can get washed away in an instant. So unlike the rock, where barnacles and mussels could attach easily to the rock, things in the sandy environment have to burrow down to protect themselves from getting battered by waves and washed away. So we can see that the clams are burrowed down. We can see that. So this is a horse clam, and that's the siphon. And the clam lives about a foot or so under the sediment, and it gains protection from just being buried. But it sticks up the siphon above the ground, and it draws water in and out with the siphon so that it can filter feed in that way. So it thinks I'm trying to eat it, and it'll retract down under the soil for protection, and it has to expel water from the siphon as it retracts. So that squirting that we saw earlier was just clams expelling water. These eelgrass beds are really good habitat for a lot of different organisms, and one that thrives here are crabs. So this is a red rock crab. They tend to be in shallower waters, and it failed to escape as the tide went out, and it's trying to hunker down a little bit into the sediment, but it would be pretty vulnerable to being eaten by a river otter or a seagull or something. Let's take a closer look. Oh, it's actually lost a couple claws, so maybe it's had a encounter already. These rock crabs have relatively big pinchers, so you want to be more careful with them than you would with a Dungeness or a small shore crab, which can't really hurt you much with their pinchers. Here's an egg mass. A lot of animals that live in the eelgrass meadows have very sticky eggs, and they'll glue their eggs to things like eelgrass or seaweed. Herring, which are spawning around now, they have really sticky eggs, but these I don't think are herring eggs. These might be rockfish or something. This low tide has exposed a large bed of eelgrass. Kruckerberg refers to eelgrass as the meadows of the sea, and eelgrass actually is a plant that evolved on land like all flowering plants, but this one moved down into the marine environment. And they can control the marine environment by changing the way that sediment flows through an ecosystem. So eelgrass creates a lot of resistance to currents and water movement, and that allows fine sediments to actually settle. So not only does eelgrass need fine sediments to grow, but it can facilitate the accretion of fine sediments in a marine system. Now, how come it doesn't just get yanked out by waves? Well, eelgrass have these long rhizomes with roots attached that keep it anchored in place. And as sediment increases in depth over the plant, it just grows a new rhizome higher up. And Native Americans actually, in many places, will eat this young rhizome, and it has a very sweet taste, and it's best eaten in the spring. Right around now. All right. We talked about the horse clam. This is a horse clam shell, and the horse clam is one of the biggest clams that we have, second only to the gooey duck, and gooey ducks are really only found subtidally. Horse clams can be found at most low tides, and their shells have these concentric rings. Now, another clam that we see here in the low intertidal is a heart cockle, and the heart cockle can be identified by both its radial ridging and mild concentric ridging, but the radial ridging really dominates on the heart cockle. Now, cockles are sort of cool because unlike most of the other clams that burrow deep in the sediment, the cockle will often be on the surface, and it can evade predation with its foot. It flexes its foot and kind of springs and can propel itself along the surface and escape a starfish that might be coming after it. What else? As we move up in the intertidal zone, we'll start seeing more of these shells, and this is called little neck clam, and you can see that the ridging on the little neck is equally as pronounced radial ridging as concentric ridging, so it has sort of a crosshatch pattern on the valves of the clam. And also, if you rub your fingernail along the edge of the little neck, you could feel the ridges. And that's important because we also have manila clams here that have been introduced, sometimes called the Japanese little neck. And when you rub your finger along the edge of that valve, they're smooth. Another clam here is the bent-nosed macoma, a much smaller clam, and it's called the bent nose because if you look at it from the side, you can see that it's not symmetrical. One side really curves up. bent-nosed clam or bent-nosed macoma. One you need to know for the quiz. I want to point out a few more bivalves. These are creatures like clams and oysters that have two shells. They're called valves. And we saw like the horse clam and the cockle down in the lower intertidal. But up in the higher intertidal, there are several other bivalves. So here's one. This is called a manila clam or Japanese littleneck. And you'll notice that it looks quite a bit like the native littleneck clam, but there are a few differences. One is that the manila clam here has more of a triangular appearance overall, whereas the littleneck has more of a square-like appearance. You can also see that quite frequently the littleneck has some radial streaking on the shell, and then this isn't a 100% feature, but frequently on the inside of the manila clams, the corners will be purple tinged. And then if you rub your finger along the edge of the valve, it's smooth and not ridged like the native littleneck. So again, this is the manila clam or Japanese littleneck, introduced as a for shellfish aquaculture. Another non-native clam is the varnished clam, purple varnished clam. It's called the varnished clam because this coating on the outside of the valve looks a little bit like varnish. And the inside of the varnished clam is very purple tinged. And varnished clams hold the paralytic shellfish poisoning toxin for a really long time, and so most people recommend not eating varnished clams from the Puget Sound because they take a really long time to metabolize that toxin. Alright, another introduced shellfish species is the oyster, often called the Japanese oyster. It was introduced in the late 1800s, actually here in the Bellingham area, and has since spread throughout the west coast. We do have a native species of oyster called the Olympia oyster, and it's generally a smaller species. And then mentioned in the tide pool, this creature called a jingle shell, and the top is kind of nondescript, bottom is smooth, and so this is traditionally used as an ornament on Native American regalia, and sometimes they're more colorful on the underside. But this actually only has one valve, it's not a bivalve. It just attaches, sucks right onto a rock. And another creature that sucks onto the rocks with a strong muscle foot is the limpet here. They look like little volcanoes. So those are the shellfish that I want you to learn for the quiz. And now we're going to take a walk along the shoreline here and learn some plants that are found usually in close proximity to the ocean. Behind me is a big outcrop of this chestnut sandstone, and this could be called a feeder bluff. Sediment, boulders and stuff might break off this onto the beach where they can get broken down into smaller pieces and nourish a beach with sands and pebbles. And some plants enjoy growing on rocky outcrops, along the coast especially, and one that I'm excited to show you is blooming right now. It's just around the corner. Follow me. This is the aptly named sea blush, and it can grow on thin soils, sometimes called lithosols. I also sometimes see it on the back shore of sand dunes. There's a variety of habitats that it can grow in. Growing just out of reach of the salt spray, but not far from the beach, we can find dune grass. And look at, here is seaweed and eelgrass that's been pushed up by high tides and wind, and this will fertilize the dune grass. Dune grass is one of our fattest bladed grasses in the Pacific Northwest, and it will grow on gravel and sand. That's why it's called dune grass, because it's often found on sand. A few of our coastal species are actually most common in north central Washington, and here is one that follows that pattern. This is called serviceberry or Saskatoon, and it'll be blooming shortly. It has these nice white showy petals, and a good feature for identifying it are the coarsely toothed leaves that are especially coarsely toothed at the tips of the leaves. Serviceberry is found throughout the US and Canada. It's actually found in every single state and every single province in North America. And in many parts of its range, the climate is quite cold. And that's one etymology, or one explanation for the name serviceberry. So in cold climates, the ground would freeze solid and people couldn't bury their relatives that died during the winter because they couldn't dig a hole to put them in. So they would wait until the spring when the ground thawed to bury everybody that died during the winter. And at that time the serviceberry was typically blooming, and so it was blooming for the funeral services, hence the name serviceberry. Another lover of dry rocky sites is this shrub here called tall Oregon grape. We actually have two types of Oregon grape. One often called low or dull Oregon grape, and this the tall Oregon grape. Now remember last time I taught you about pinnately compound leaves, and this is another example of a pinnately compound leaf. We can see that these are leaflets and they attach along a stem or a line. Now the leaflets on dull Oregon grape look a little bit like holly leaves, and for that reason it has a scientific name that's similar to holly. Holly is Ilex aquifolium, and this is Berberis aquifolium. And the leaves tend to be kind of shiny with a little bit of a leathery look. And the flowers, brilliant yellow, and you could eat the flowers. They're sour. They're a little bit bitter also. It'll fruit with blue grape-like berries, but they're very sour and not as sweet as a grape is. So this is our tall Oregon grape. Look for it on coastal bluffs and bald habitats. Beside me here is Nootka rose. Now Nootka rose is a thorny rose, like most of our roses, and the thorns tend to be quite large, straight, and just below the twigs. So here's a twig, two thorns below it. Here's a twig with two thorns below it. Here's a very small twig with two thorns below it. So you can see the pattern. The leaves of Nootka rose are pinnately compound. So here's one leaf with 1, 2, 3, 4, 5 leaflets, and serrated leaf margins, which means sawtoothed leaf margins. And Nootka rose has what's called a hip or a fruit. This is last year's, it looks terrible, but it's a little bit like an apple in that it has a fleshy part with the old flower at the tip. Last year's sepals are browned at the top. So Nootka rose is one of two common roses that we have in western Washington, but Nootka rose is more commonly found on the shorelines, whereas our other species, bald-tip rose, is more common in more woodland environments. So quite a few shrubs so far, and that's sort of curious. Why so many shrubs near the coast? Well, one reason is that there's a lot of light coming in from the ocean. It both reflects off the water, and there just aren't trees on the ocean side of the coastline, and that sunlight that penetrates into the forest edge provides a lot of nourishment for the shrubs. Our next plant is ocean spray. This is a quite tall shrub, and it just has simple leaves. They look sort of like an oak leaf. and the last year's flowers are still clinging to the plant, and they're all dry now, but they look kind of like dirty socks at this point. Ocean spray is also sometimes called ironwood because the wood is very dense and doesn't catch on fire easily, and is used for barbecue sticks, hot dog roasting sticks, that sort of thing, as well as arrow and spear shafts by Native Americans here in the Salish Sea region. Climbing all over this ocean spray bush is a plant called orange honeysuckle. Now this is a vine, so it doesn't really have enough woody tissue to support itself, but it twines around the plants and gets up into the canopy enough to get sunlight. So this is one with opposite leaves, like remember the maples have. All honeysuckles have opposite leaves. And it has a brilliant orange flower that will be blooming shortly. I expect in a week or two. Beside me is a crabapple tree, and it's a little hard to identify right now because the leaves are still coming out, not full size. But I thought a little bit of description is better than none, and you could look for pictures online. So here is the crabapple leaf, and one thing that distinguishes our native crabapple from the introduced apple that we eat from the grocery store is that the crabapple leaves often have lobes. So we talked about serrated leaf margins. Another feature of leaves could be lobes, like a maple leaf has 5 lobes, an oak leaf has kind of oak-shaped lobes. This one has kind of thumb-like lobes, except there's one on either side. Sometimes it'll have no lobes, and sometimes it'll just have one of those thumbs, but this particular leaf has 2 lobes. So the crabapple, when it produces fruit, it usually will produce a cluster of them all together. The apples have fallen off, but you could see where they were attached. And they're quite small, usually about the size of your thumbnail or smaller. And here's one from last year that's all dried up. Now, crab apples are very edible, but they're also very sour. I enjoy eating them in the fall after the frost has softened them and made them a little bit sweeter. And Quaxistala, my mentor that I've shared a story from already, he called this the stage when the apples turn soft in the fall, kumduch, and he said that's when they're best to eat. And if you weren't going to eat them in the fall after the frost has softened them, you should store them in water and soak them for a month or so before you eat them, and that removes some of the bitterness and just gives you sweetness and tangy sourness in the crab apples. Down here at Larrabee, there's a cool weathering feature on the sandstone, and a professor at Western actually wrote a paper on this and was the first to describe it to the scientific community. But he was wondering what was going on with the sandstone honeycomb patterning. What patterns could be found, and so he mapped it out wherever it was found, and it turns out it was always found close to the ocean on south-facing slopes. And so these are some important clues. And after doing some analysis of at a very fine scale, looking at the pores in the sandstone, also learned that there's a lichen that grows in between the grains of sand. And so the full story is that seawater can spray and erode pockets of sandstone, but there are lichens that form around the outside that make the sandstone harder and keep the erosion from happening. And so it needs to be in a place where there's sea spray to erode the insides, and it needs to be in a place with southern exposure for the lichen to form. So this pattern is called sandstone taphony, or honeycomb weathering. But if you want to use the fancy word, you could say sandstone taphony, T-A-F-O-N-I. Along our coastline, we occasionally get a neat plant called soapberry or buffalo berry, and I spotted one up here. So I'm going to climb up and grab a piece of it. Soapberry is one of those species that's more common in north central Washington than it is anywhere else, but it does show up here right along the coast. And it is a dioecious plant, which means that it has flowers that are either male or female, and those flowers are found on separate plants. So this is a female plant which will produce berries eventually, and somewhere else hopefully there is a male plant that is close enough that these flowers can be fertilized. But some interesting features of the soapberry are the glandular dots that cover the leaves, and this too has opposite leaf formation. One tree species that actually loves growing along the coast is one called arbutus or madrona. And above me here is a madrona, and they are an evergreen tree. They keep their leaves all year round, and they can't compete with the Douglas fir for growing tall and getting access to the sun, but they can grow at all sorts of weird angles to reach out and get access to the sun. So they commonly grow on the tops of rock bluffs and lean out over water as a strategy for getting sun.
I went up to Drayton Harbor and Blaine to get footage of a few of the shoreline and pelagic birds that are in the study list. Many of our gulls are scavengers that will fly along shorelines looking for food opportunistically, and here are some glaucous-winged gulls that have found a little neck clam and dropped it on the dock to break it open so they can eat what's inside. Now, glaucous-winged gulls can eat just about whatever they could get down their mouths. I've seen them spend 10 or more minutes trying to swallow a starfish. Pelagic birds are those that dive into the water column to feed on fish. And here's a common loon in brilliant breeding plumage. Now, the common loon has special adaptations for diving. It has solid bones instead of hollow bones like most other birds, and the feet are located very back in the very back of the bird, which enables it to swim much better underwater than feet that are located more along the midline of the body. The redneck grebe has very similar adaptations, but lacks the solid bones, and we get a nice look at its feet when it dives. I'll end with one last plant.
Salal is an evergreen shrub that seems to grow everywhere along the coast. It has these broad leaves that are simple, and it produces a berry that usually ripens in August or September, and it's quite tasty. So look for it close to the shorelines. It'll grow further from the shorelines as well, but like many of the plants I've mentioned, it really benefits from more sunlight being close to the shore. So that's most of the plants I want you to learn for the quiz, but there are a few others like bald tip rose that I didn't mention. You're on your own to study that one. So see you next time.